We set up the experiment where we would shoot into a motion capture arena at about 6 meters per second higher, 7 to 8 meters per second. We put a piece of wire across the lab about 3.5 meters away, and we made sure that the trajectories didn't last more than a second, just so it didn't like fly around the room and get rid of its energy that way. And the claim was, in order to accomplish this, to land on the perch with those specs, you had to be exploiting a pressure drag. Okay, and we can do that now. We can do it pretty robustly, pretty efficiently. This is slowed down about 11 times. This is the plane being launched in. It's now at an exceedingly high angle of attack. This is the wire thrown across the room, and we can land on a perch reliably now. About 19 out of 20 times from a pretty huge range of initial conditions, indoors. Okay, so this is just to show another couple of videos of it. The hardest part of once we got it working, the hardest part was getting these high-speed videos without interfering with mocap because of the lighting conditions and everything. But we have a few videos of it landing nicely. We got together with Mark Koski's lab at Stanford, brought some of his perching spines over, and we can do the same controllers to land on a wall. The Air Force wants us to land on a power line to trickle charge the batteries. It turns out there's always people that wanted perching aircraft. We just thought it was a fun problem, but it turned out to be kind of a fun problem for applications too. Okay, so that's one example of the type of control problem I want to talk about trying to solve. Just to convince you that it was hard, that we were in a difficult dynamic regime, here's a smoke visualization of the perching plane during flight. We just released smoke from the leading edge, and you can see that the wake is dominated by these vortices that are shed off the back of the wing.
Was that closed loop control? Or?
It's absolutely closed loop. It does not, I mean, open loop would just miss the perch every time. Yeah. And I'm going to tell you the story about how we make that controller. So the experiment sort of demonstrated that the post-stall flow does not imply a complete loss of aerodynamic control, or control authority. A lot of people sort of assume that your post-stall, your control authority is gone. It's certainly diminished. It's more complicated, but you still have some authority. And in an experiment, we get about 4 times more drag scale than the best runway landings, just because we got a foam plane that we're willing to go up into really high angle of attack and do these experiments. Here's a completely different example from the other side of my other world of walking robots. This is a little dog robot. This was built by Boston Dynamics to be a miniature big dog. Unlike big dog, it's got motion capture markers. It walks on known terrain, and it's expected to go over terrain that's a significant fraction of its life length. Big dog moves around blind. Little dog's supposed to plan over very complicated terrain. And in fact, early on in the program, this was a DARPA program. A number of schools got these little dog robots. We're forced to race our dogs every month, which wasn't great. But you'll see at the end of the videos, we always dive for the gold just to try to beat CMU that day, right? So, but by the middle of the program, people were doing pretty well.